Thank you for the introduction. My name is Siyang. I also go by Sean. I'm from the Johns Hopkins University and the SHOES team. So the title I submit is a little long, so here I'm going to abbreviate it. I'm going to talk about JWST observations, distance measurements, and a new tool, the J region asymptotic giant branch, or the JAGB. And so I first want to give a review and introduction to the current state of the Hubble tension in terms of direct measurements of the Hubble constants. So at the moment, the gold standard for measuring a direct value of H0 comprises of using a 3-rung distance ladder. This involves using geometric distances, such as parallaxes or water masers, to calibrate the intrinsic luminosities of Cepheids variables. We then use that information to measure distances to galaxies that host both Cepheids and type 1a supernovae to calibrate the intrinsic luminosities of those supernovae. We then in turn use that to measure distances to galaxies further in the Hubble flow to measure the Hubble constant. And over roughly the past 15 years, the Hubble Space Telescope has allowed us to calibrate roughly 32 type 1a supernovae using 4 geometric anchors. And this allows us to reach almost a 1% measurement of H0. Now this value is in almost 6 sigma tension with the Planck lambda CDM model. All of this data is public, and there have been many reanalyses of this data. At the moment, there's no evidence of some systematic error in this analysis that might solve the Hubble tension. And I do encourage you to read the review paper by Verde, as well as take a look at this compilation of different studies looking into the systematics in this GitHub link right here. Now, the launch of JWST has allowed us to check this HST link. And at the moment, with the data we have, we do see very good agreement between the JAGB, TRGB, and Cepheids distances. But I do want to first note here that we do have to be cautious in that with JWST, we have very few samples. And really, we can't really resolve the tension. So, trivially, if you increase the errors, you also decrease the tension. And you also introduce large fluctuations in that measurement. And so I would say that we really need to wait until we have more observations with JWST until we can really resolve the tension. So next I wanted to show a plot from the review paper by Verde showing the state of the tension in different measurements. I do want to note that the tension is data-driven and is not exclusive to any one method, source, or team. As you can see here, there are many points that are in the tension. It's very difficult to resolve the tension on the direct measurement side without avoiding, discarding data, picking one study over another, introducing anti-Copernican ensembles, etc. And so I do encourage you, there will be a book, The Hubble Constant Tension, led by Eleonora, as one of the editors. That should be coming out soon. I do encourage you to contribute to the CosmoVerse white paper as well. So now I want to move on to the J region asymptotic giant branch, or the JAGB. And so the JAGB refers to this overdensity or clump of stars, shown here in our near-infrared color magnitude diagram. And this region contains these thermally pulsating carbon-rich AGB stars. Now it's been proposed in the literature that some sort of mean or median or mode or model fits of the magnitudes of these carbon stars can be used as some sort of standard candle. Now the argument for this lies in the expectation that your star has to have a mass that lies within a relatively narrow mass range in order for that star to be carbon in the first place. If it's too massive, bond burning will occur and carbon will burn before it reaches the surface of the star. If there's not enough mass, the third dredge-up events will be too weak to bring enough carbon to the surface. Now I do want to note here that this might not actually be the entire picture, and I'll talk about that more later on. So observationally, measuring the JAGB involves only single epochs of visits. What's convenient here is that we can isolate the J region to measure the JAGB with simply using color cuts. So for instance, you can apply a color cut of J minus K of 1.4, 1.5, vertical cut here to separate out the F and J regions. And you can also apply a color cut at 2 to separate out the J and K regions. Now we were able to measure and observe this JAGB region using our JWST Cycle 1 program 1685. That program had targeted maser host NGC 4258, which we'll use to calibrate the intrinsic luminosity of the JAGB, as well as 4 galaxies that had hosted type 1a supernovae. including NGC 1448, 1559, 5584, and 5643. So for all the JGBs, I'll be measuring in these galaxies. I'll be doing that in the JWST F150 and F277W filters. And so the JGB, as a relatively new standard candle, does seem to be very promising based on the literature. But how standard is it really? I'll be checking this. There have been several methods proposed to measure the JGB reference magnitude, including the mode, the mean, the median, or the model fits. I'll be comparing and using many of these. And finally, I'll be comparing JHB distances to our host galaxies and comparing those to the Cepheid, TRGB, and Miras distances, all calibrated to the same anchored galaxy. So here I'm showing the footprints for our observations. Again, on the right here, we have 5 different galaxies, including the major host NGC 4258. You might notice that we have 2 visits for each galaxy, and that's because these observations were also designed to measure Cepheid variable fit. We perform photometry and crowding corrections using the JWST software and apply foreground extinction corrections following the Schlafly and Finkbeiner dust maps. And so I first wanted to pause and take a little time to describe how we're going to try to avoid confirmation bias in the context of running the photometry. And so we run our PSF photometry using the JWST software, which is canned, and that the routines and the parameters are already specified in the JWST NIRCam manual. We do not perform any iterations, meaning the photometry is performed once, and that's before any analysis. Now there are practices like blinding, where you can add or subtract a random constant to your photometry, or compartmentalizing, which is what the SHOES team does, where you run your photometric pipeline on your frames without any information of the Cepheids. But I would say these steps really do give a false reassurance, since this photometric pipeline is really automated. If you're following the procedure correctly, there's not really any knobs you can turn. So I would argue that instead, open access data, in terms of providing the photometry, as well as transparency, is really key for avoiding and identifying confirmation bias, as well as building community trust. And so Adam Rees said something that I thought summarized this very well. Blinding and compartmentalizing is something you do to trust yourself. Open data and reproducibility is what others need to trust you. So now I wanted to move on and start to introduce how we're going to measure the JGB. And so we have our JGB clump, and here's a plot I'm showing from the Zagorski paper. And what's been done in the literature is you build a box around that clump to isolate the J region to measure the JGB magnitude with. So as I mentioned before, there have been several methods proposed to measure the JGB reference magnitude. These all seek to identify some sort of peak in that luminosity function, or histogram of magnitudes of those carbon stars. These different methods include using the mode of a smooth and bin luminosity function. You can take the mean or the median magnitude. You can also fit a model, or adopt some alternative definition of the median. And so I do want to note really quick that the mode does require both binning and smoothing, and you'll be seeing more of that later on. And so a priori, we really don't know what is the best method to measure the JHB width. And so this leads to the possibility of several measurement variants. And that's what we're going to adopt. So in our study, we're going to look at several measurement variants. And so we adopt 5 different color ranges, as well as 5 different summary measures. And these summary measures include the median, the clipped mean, a mode with 2 different strengths of smoothing, as well as a model fit. And this results in a total of 25 different combinations. Now we did look at trying to change the binning variance for the methods that require that, although we found very little difference. So the first thing that we really wanted to look at was how much does the JHB vary field to field? And so for a good standardized candle, we would expect that the magnitude of that standard candle should not vary significantly depending on where you look in a galaxy. And that's provided you're looking in the same general region, like the outer disk for the JGB or the halo for the TRGB, for instance. And so we first looked at this using NGC 4258. And on the bottom left, I'm showing the footprints again. We have this B module corresponding to the NIRCam instruments on JWST on the east side, as well as the A module corresponding to the west side. And on the right-hand side, I'm showing the color magnitude diagrams together with the corresponding luminosity function. So again, there's histograms of the magnitudes for the stars in the J region. And I do identify, or I do define a few different regions, which I'll talk about later. So the inner region will correspond to the B3, B4, and A3, A4 regions. The outer region will correspond to the B1, B2, and A1, A2 regions. And so the color magnitude diagrams on the right here, we can immediately see several different things. One thing to point out is that luminosity functions are very asymmetric. In addition, the mode JGB, using a smoothing of 0.25, don't all agree within their statistical uncertainties. So one of the tests that we performed was comparing the JGB measurements in fields that are on opposite sides of a galaxy. And so the first test that we performed was measuring the JGB in the B1, B2 field, comparing that to the JGB in the A1 and A2 fields. Now the expectation is, again, that if you measure the standard candle in those two fields, ideally they shouldn't differ significantly. On the plot on the right, I'm plotting the difference in the magnitudes between those two JHB reference magnitudes as a function of the variant number. And again, we have 25 different variants. And we can see immediately that a lot of the variants are clustered around a non-zero value, maybe about 2/10 of the magnitude. And a majority of them are not consistent with zero, which what we would expect for a good standard candle. Now, if we repeat this for the inner areas, in this case it's B3, B4 versus A3, A4. Although we have more stars in this case, we do still see this non-zero difference. And finally, we took both outer modules. So we compared the entire B module and compared that to the entire A module. And even with the most, best handle of the number statistics, we do see non-zero differences. Because the differences are certainly outside, much greater than their statistical uncertainties, this may suggest that something intrinsic might be going on. So we performed a similar test in NGC 1448 and 5643. And here we tried our best to construct those opposite symmetric fields. 1448, we simply just drew a line down the axis of symmetry, down the galaxy, and for 5643, we just took the fields outside the galaxy. And we can see from the color magnitude diagrams on the bottom that we see something very similar as we did before. For 1448, we see that the mode magnitudes don't quite agree. Although interestingly, for 5643, the magnitudes actually do agree quite well. And so when we plot the same comparison as we did before, again comparing the two fields as a function of 25 different variants, for 1448, we do see that, again, there are lots of differences that are not consistent with zero, maybe centered around 0.05 magnitudes. But for 5643, we see that most of those variants are actually consistent with zero. And that suggests that this field-to-field variation might behave better or worse in some galaxies compared to others. Now, you might have noticed that sometimes, the mean might be very different from the model fit or a mode. And that's because the luminosity functions of the J region have this non-uniform asymmetry that inevitably causes differences between measurement methods. For instance, if your luminosity function is symmetric, your node will agree with your mean or your median, but if you have an asymmetric luminosity function, your mode will be different from your mean and your median. Now, in particular, in NGC 4258, we do find that the mode and the mean can differ by almost 3/10 of a magnitude. We do find non-zero differences, although to a lesser extent in our supernova hosts. We also sought to see if this similar pattern occurred in the ground-based data for the Large Magellanic Cloud and the Small Magellanic Cloud. What we did here is to measure the JHB reference magnitude in these two galaxies, took the difference between those two JGB reference magnitudes to compare those to the geometric distances, the differences in the geometric distances determined via the detached eclipsing binaries. And that geometric difference would be essentially the gold standard that we would compare to. We do this both in the J and the H band, and we do find, from here in the plot on the bottom right, that most of the measurement variants don't quite agree with the geometric distances. And that's something that definitely the ground-based studies should look into some more. So the next thing I looked at was seeing how the JHB varies as a function of angle. And so this uses the same principle as before. We're trying to see how does our standard candle magnitude vary as a function of where you look. And so what we do here is, what I'm trying to show here is we construct a 90-degree window of the galaxy. We measure the JHB reference magnitude in that window, and then simply rotate that window 360 degrees. Now here's what the results look like. We did this for 1559 as well as 5584, which had fields that allowed us to do this. So in the y-axis, we plot the magnitude of the JHB reference magnitude. We do that as a function of angle. For each galaxy, we look at 4 different measurement types. So that's 2 modes, as well as the mean and the median. And we see here that we have variations on the order of maybe 1/10 of a magnitude. And these are certainly much greater than the statistical uncertainties, suggesting that something intrinsic might be going on. So with these variations in mind, we then measured distances using the JGB. So on the right-hand side, I'm going to show the distance moduli as a function of the variant number. Again, like 25 different variants. The red line shows the median value out of all of our 25 measurement variants. I'm showing in the blue line the Cepheid distance from the REES 2022 paper that's adjusted to having an NGC 4258 anchor-only distance. We also look at the TRGB distance in orange from the extragalactic distance database, as well as the Miras distance in cyan for 1559. And I would say in general, we do see broad agreements, but there is this methodological variation that arises due to the unequal asymmetry in the J region luminosity function that spans almost 2/10 of magnitude. And this would be the biggest systematic in an H0 measurement. And so we decide for our H0 measurement to incorporate these variations. We find an H0 of roughly 74.7 plus or minus 3, about, with a full range spanning 71 to 78. And so I've been talking about this asymmetry and variations a lot. And so you might be wondering, where does this asymmetry come from? And I want to note that the asymmetry in this J region luminosity function has been independently observed by other teams as well. Here I'm showing a plot from the Prada 2021 paper that shows that their luminosity functions that clearly shows different levels of asymmetry in their luminosity functions. Now this could potentially be attributed to different metallicities, and that different carbon stars with different metallicities might have different mean magnitudes, although this is at the moment not well calibrated. Now another possibility is that we're simply looking at mixed population of stars. And so the proposed 2020 paper showed that in the J region, there exists these N-type and J-type carbon stars. And so what we did here is we took this sample from the Abia 2022 paper and plotted the luminosity functions for these galactic carbon stars and separated out the N-types and the J-types. What we found here is that when you separate those N-types and J-types, they do have luminosity functions, or again, histograms, that have means that are not quite consistent with each other. And one important thing to note here is that the J-types are extrinsic carbon stars, meaning that they get their carbon from a companion star. This also means that the extrinsic carbon stars do not follow the typical argument that you have to have a mass within a certain mass range in order for the carbon star to be carbon in the first place. Now, qualitatively, we can see that the J-type luminosity function does behave a little less, uniformly. There's a larger range compared to the N-types, although, of course, more stars would certainly make this comparison clear. So now I wanted to start wrapping up and talk about some future directions that we might head in. And so one thing that will be very important is to really build a comparison between these distance indicators. So comparing Cepheids and tip of the red giant branch and the JGB. And so for TRGB and Cepheids, at least, studies and papers, such as the one by Friedman and Medor, have seen very good agreements between Cepheids and TRGB. With recent JWST data, we have measured very preliminarily the I-band TRGB, or JWST F090W TRGB, in 7 host galaxies, and we do find very good agreement with the HSD Cepheids. And from the available samples that we have in the data, at the moment we find no significant evidence of a difference between HSD Cepheid and tip of the red giant branch distances. And that's something that's a very common misconception. Now, fortunately, we do have a lot more data coming in from various teams. And another very important thing, I think, is to really look into the field-to-field variations of the JAGB. Now, unfortunately, with JWST, we really don't have enough fields to really fully characterize this, but it'll be very important to really understand where does this field-to-field variation come from. This would be similar to what the comparative analysis of TRGBs or CAT's team did for the TRGB, where they looked at multiple fields in a galaxy, here for NGC 4258, measured the TRGB in each field, and observed what differences they were. And they found that something called a contrast ratio could actually better standardize the TRGB. And so future missions, such as Roman Space Telescope with a wider field of view, as well as more JWST observations, will certainly help characterize this more. And so just to wrap up really quick, so in the study, we did investigate the standardization of the JGB, and we found evidence of field-to-field variations as well as non-uniform asymmetry in the J region luminosity functions. And this causes variations in the distance and H0 measurements. Now, we broadly do see agreement with Cepheids and TRGBs, although the uncertainties are very large. But these variations really need to be either accounted for in the error budget or ideally standardized sometime in the future. Again, I do want to caution that with JWST, we really have a very limited subsample. And we have very limited subsample and only one anchor to work with, NGC 4258. H0 we find here is 74.7, but again, we have a full range of 71 to 78. All in all, I do think the JGB is very promising, although it needs to be standardized further. There's a lot of more work that needs to be done, but I think that's natural given how recent and new this method is. And so I do look forward to future missions like Roman, more JWST observations that'll hopefully make this standard candle more competitive with other distance indicators. Thank you.
A question or two. Yes, Lorena.
You correct your observations for the extinction in our galaxy, but you always use the same extinction law independent from the direction. I think even in our galaxy, the extinction curve does depend on the direction, although I'm not sure what are the spatial scales for those changes, but maybe it's worth really checking.
Mm-hmm. Right. And so I think we do have, our group is also working on looking at possible variations in the extinction law. And we are seeing that, at least for the directions in the host galaxies that we're looking at, it doesn't vary significantly from our vehicle 3.1.
It's an extension of what I asked you over lunch. You said that the magnitude differences for JAGBs are about 0.1. And I was wondering if you can tell us a little bit about, compare that to the magnitude differences you find for Cepheids within the same galaxy, Miras, and TRGBs, and also how those translate into delta H0s.
Right, and so, sorry, just to clarify, so we talked about TRGB with a variation 0.1 during lunch. Is that what you're talking about?
I guess I'm just asking, so you're saying that within one galaxy, you're seeing variations of JAGB magnitudes, right?
Yes.
And I wanted to understand how that translates to an uncertainty on H0. So what you have here is you're showing me an H0 plus or minus 2 to 3 is what you're getting. And I was wondering how that compares to magnitude differences found in Cepheids or TRGBs, which we assume usually are much cleaner calibrators that we have just accepted are good calibrators so far, and I was wondering what the magnitude differences and the delta H0s are like for those calibrators.
Right, thanks, that's a good question. So for the there's two effects going on right here. So there's a field-to-field variation as well as a methodological variation that we see here. And so the TRGB from what the CATS team found was that there was this field-to-field variation that existed in the TRGB measurements as well. And so what they did was they further standardized that. So they introduced something called a contrast ratio that can better standardize the variations in those. And so we do also see those field-to-field variations in the JGB, although at the moment we really haven't seen, or we don't have a really good standardization method to account for that at the moment. The other effect is the methodological variations that the TRGB doesn't have yet. So the TRGB typically use one method. You can use a Stillwell filter or maximum likelihood estimation. The JAGB, we're using different variants here, and we do see different variations across those variants. And that's something that the TRGB the method at the moment doesn't really have. And so these variations, so we do incorporate, in Cepheids, of course, there's just one way to do that. You don't have to choose between like Sobel and maximum likelihood for like what you do in TRGB. And so in terms of H0, so we do see this large span in the methodological variations of almost 2/10 of the magnitude, so plus or minus 0.1, both directions. In terms of H0, we adopt that as this systematic uncertainty and translate to roughly 2, a little over 2 in H0, plus or minus.
It wasn't a question as much as I was just going to chime in with what Sean said in the last answer, just that the difference, I think, for Tanvi, if that's who I heard, was that what Sean is talking about have been systematic. So the issue of the asymmetry or the tip contrast ratio for TRGB. Whereas I think in the case of Cepheids, because we have periods, then they are more tightly calibrated. So it's not systematic, it's, that's more statistical noise that we have.
Thank you.
So,
right,
thank you
thank you,
everybody.